Welcome to trees, and I have two trees for you, and we're going to talk about both of these trees. On the right, we have a rooted tree. You can see this tree has roots, and their roots are in the ground. On the left, you have what this video is dedicated to. You have a free tree. This tree is not restricted by the ground, although roots have a purpose, so maybe this tree is going to die. Also, gravity is a thing, but let's not worry too much about that part of the metaphor. We have free trees and rooted trees. We'll talk about free trees first. Free trees do not have roots. Again, I guess technically this still has roots. They're just not in the ground, but don't think too hard about this picture. So there's a little bit of controversy over here, so hope we don't start any fights in class, but there's a little bit of a controversy of when we just say tree. What's more basic, right? Like, does tree imply free tree or rooted tree? And different authors do different things. So I'm going to try to always specify, just like the book tries to always specify. But yeah, if you see online or in other sources, just tree, they might be talking about a free tree. They might be talking about a rooted tree. You're going to have to figure it out. Don't step on any toes. Oops, not that yet. So let's start with a quick definition. Trees are just graphs. And specifically, a free tree is a connected graph. That's very important. It's a connected graph with no cycles. And that's all it is. So these are the two requirements. All right. I also highlighted the definition. But the connected and no cycles, it's just a graph. It's a special kind of graph, and it's nice because there's lots of fun things that we can do when we have a tree. You want an example of what a tree looks like? Well, yeah, this is what a tree looks like. But in terms of structures, what does a tree look like? It looks like this, right? I said this was also called a minimal spanning tree. This is a tree. It spans the whole graph. It covers the whole graph. And specifically, it has no cycles and it's connected. There is no way to get a cycle in these blue edges. It is a free tree, specifically. The next video, we'll talk about what is a rooted tree. So as another example, we're going to do a couple of questions with this free tree over here. It's a simpler version of a free tree. Pretty self-explanatory. We got 6 nodes, A through F. So what I would like you to do is pause the video and answer these questions. I want you to answer these questions and see how you can work with these definitions and see if we can get anything from these ideas. So first off, are there any two nodes that have 2 paths between them? So just, start picking 2 nodes, right? If we look at these 2 nodes, how many paths are there to get from F to D? There's only 1. Well, if we choose these 2 nodes, how many paths are there to get there? Well, there's only 1. Are there any nodes that have 2 paths between them? And the answer is no. And there never will be. Specifically, trees have the property that every node only has 1 path between them. Sorry, every pair of nodes. Every pair of nodes has only 1 path connecting them. That's true for all free trees. And again, it's true for here. Any 2 nodes in this supply line, there's only 1 way to get there on the supply line. And that makes sense, especially in context of this algorithm, right? We wanted the cheapest thing, and so we don't want redundancies. All right, find an edge that you can remove and still have it be a free tree. And you can play around with this, but right, any edge that we remove, if we remove this edge, it's not a free tree. Why not? It's not connected. Remove this one. Nope, not connected anymore. And again, this has to do with redundancies. Trees don't have redundancies in general. every edge we have, we need. There's no edges that we can remove and still have this be a free tree because we lose it being connected. So you could say there's no redundant edges in a free tree, but I'm just going to say, right, yeah, it would lose the fact that it's a connected graph. Similarly, right, any edge that you add is going to break it. Any edge that you add is going to make it cyclic. All right, there is no edge that you can make that does not create a cycle somewhere. All right, so again, there are none. Every edge that we add, it won't be a tree anymore because it is going to become cyclic. How many nodes and edges are there? Well, there are 6 nodes and 1, 2, 3, 4, 5 edges. And that is always going to be n minus 1. And again, it has to do with no redundancies. If there are 20 things and we need to connect them with as few edges as possible, there's going to be 19 edges, and so on. So these are some properties. Hopefully you can think about them, and they hopefully make sense. Some properties of trees, and we'll talk about rooted trees in the next video.